Hi, my name is Eric Bliss, and I'm an instructor here at Purdue Global. My background is in nuclear chemistry. Specifically, my doctorate is in environmental chemistry, but that's only because nuclear chemistry didn't exist as a subset where I was at the University of Tennessee. I chose the University of Tennessee because I didn't do any of my research at the university. It was all at the Oak Ridge National Lab, just 45 minutes away. And for those that don't know what national labs are, it's one of the 7 places you can basically handle real hot stuff. And by hot, I mean very radioactive. So more than just tracer quantities, I was working with some pretty heavy duty stuff, fission grade plutonium, fission grade uranium, isotopes along those wayabouts. And I've been in administration for the last 15 years. And the only thing I've consistently taught has been a nursing chemistry course, which does cover this exact topic. But definitely my expertise is more within nuclear chemistry than it is, say, nuclear chemistry applied specifically and only to the health sciences. But certainly I know enough about this topic for what we're going to cover tonight. And I welcome any and all questions, because anything I can't answer or that I screw up, I can always go find out and get more information to you, because I know what I'm looking for and I know what I'm looking through. So my phone number, if anyone wants to reach out directly, is 830-220-4109. That's my cell phone. And of course, you can reach me at Purdue Global, and I believe my email address there is eric.bliss@purdueglobal.edu. So that being said, we'll just kind of jump into it and see where this lands us. We'll go to the next slide. I've got my handy slide operator. So we're going to start off with a brief overview of the importance of nuclear chemistry in medicine. I guess advance to the next bullet or slide. So obviously nuclear chemistry plays a pretty important role in modern healthcare. And when we talk about how we apply it in healthcare, you've got both therapeutic methods and then you have diagnostic methods. So right away, it helps to define those terms. When you're talking about a therapeutic application, you're talking about something that's actually treating the illness or the problem. And when you're talking about a diagnostic application, now you're talking about using nuclear chemistry to actually diagnose, just like it sounds, right? It's to actually identify what the problem is or perhaps where it is. So that's really important to understand. Obviously, when you talk about therapeutic applications, you're talking about general and targeted cancer treatments. And when you're talking about diagnostic stuff, now you're talking about imaging techniques. And then you've got kind of a side bit where we'll use radiation to just sterilize medical tools and stuff. So it used to be, you think of sterilizing tools through hot water. And then sometimes they use UV light, like really strong UV light. Those are the cheaper methods. But there are some things that will actually just smack some x-rays and gamma rays at something to make sure it's really clean. So that's where the sterilization stuff comes from. And this is a field that is constantly growing. So the things that we're doing are getting more and more specific. And when I mean specific, I mean we're getting better at treating the actual problem and without as many side effects, because we're not hitting as much of the healthy tissues as we are the tissues that we really want to get rid of, which in almost every case, we're talking about cancer here. So next slide. Understanding radioactivity. This is a fun one. Next. So isotopes are elements that basically have a different number of neutrons, but they're the same element. So when you look at something like hydrogen, the most common form that's on this planet is basically 100% hydrogen 1. And when we say hydrogen 1, the 1 refers to the weight of that hydrogen. Now, because a proton weighs 1 and hydrogen's isotope 1 already has the 1, that means it has no neutrons. And so really, when you think of hydrogen, the element or an atom of hydrogen, is just a proton that happens to have an electron around it. That's what makes it a neutral atom of hydrogen. And of course, neutral atoms of hydrogen you'll never find in nature. They're always found as bonded together as a diatomic. So you'll have H2 as in a hydrogen gas. They each basically come together, share the electrons, so they're able to fill the S shell, and by doing that, you end up with H2. And that's considered H2, where both hydrogen atoms are hydrogen ones. That's just stable, happy hydrogen. You can also have hydrogen that has a neutron in the nucleus with it. Now we're talking about hydrogen 2. Hydrogen 2 is still hydrogen, it's just heavier. And hydrogen 2 specifically, we have a nickname for it, or a common name, and that common name is deuterium, which some of you probably have heard of but didn't know quite what it was. So deuterium is just a heavy form of hydrogen because each hydrogen atom in deuterium has one neutron in it, whereas regular hydrogen has none. And then there's one more isotope of hydrogen that exists, and that is hydrogen 3, that has 2 neutrons in the nucleus with a proton. And we call this one tritium, which is also something you've probably heard of, but never quite knew what it was. So the real interesting thing about isotopes, and I can't emphasize this enough, and you're going to hear me continue to emphasize it again and again and again, is that hydrogen 1, hydrogen 2, and hydrogen 3, they are isotopes of hydrogen. They're all hydrogen, which means they behave the same chemically. So you can't just create hydrogen 2 and hydrogen 3 and separate it from anything. Like, you can't create it chemically. You're not making and breaking bonds when you talk about different isotopes. You're actually doing something in the nucleus to make this stuff. So you're changing its nuclear properties, not its chemical properties. And because the chemical properties are the same between isotopes, that means all chemical separations are off the table for trying to create things with these isotopes. You have to use different means. And so it's not an easy thing to do. I'll just leave it at that for now. Radioactivity is what happens when you take a nucleus and you go from stable, like hydrogen with no neutrons, and you go to unstable, which would be hydrogen with 1 or 2 neutrons. And this applies for all isotopes of all elements. There will always, well, not always, but for elements that are under 82, with the exception of technetium, they all have stable isotopes. There's at least one stable isotope, sometimes 2 or 3 stable isotopes, where when I say stable, the nucleus is stable, and so it's not emitting radiation. Not emitting ionizing radiation. Radioactivity is ionizing radiation. This is radiation that involves radiation that's of such a high energy that it will kick an electron off. Like, as stuff exits the nucleus or as things change in the nucleus, it will emit a gamma ray, or you can kind of call X-rays still ionizing radiation, though we tend to think of ionizing radiation as being gamma and higher. X-rays are still energetic enough that they can kick off a few things. So that's ionizing radiation. And when you get rid of this stuff, it still isn't changing the isotopes it's coming out of if it's just releasing an X-ray or gamma ray, but you can emit other things too, like alpha particles or beta particles, or sometimes you spit out a neutron, or sometimes your nucleus will split in half. And I don't mean like equal halves, but they'll split into 2 different parts. And when that happens, you're talking fission if you're talking about splitting apart. You can also absorb a neutron, or you can absorb an electron, or just emit an electron. So let's go to the next slide. I'm going to see what else I have on here. Okay. So I'm going to go back to the slide we were on. When we're talking about alpha, beta, and gamma particles, just know that when you emit a beta particle is nothing more than an electron. And we usually say the word beta particle to refer to a negative electron, but really beta particles fall into 2 categories. You can have a negatron and you can have a positron. A negatron is a negative electron, which electrons are normally negative. That's when it gets kicked out of a nucleus. And when it gets kicked out of a nucleus, the nucleus is going to change into another element. That's another key point. So when you get rid of radioactivity, with the exception of gamma and X-rays, you're going to be changing yourself from one element into another. Kick out an electron, you're kicking it out with so much energy that it's easiest to think of it as speed, and momentum. That's how we look at kinetic energy, right? It's 1/2 mv squared. You can also consider the equation E equals mc squared because energy is related to mass and the speed of light. So generally speaking, when we kick an electron out of a nucleus, it's leaving the nucleus at like 0.1 to 0.2 times the speed of light. It's moving fast. It's moving so fast that everything it goes by, it strips stuff from it and it ionizes the air. It'll literally strip other electrons around it away. And when it runs into something, it imparts quite an impact because it is moving so fast. It's so energetic. So think of beta particles as being either negative electrons or positive electrons. And depending which one of those it emits, you're changing into something different. Alpha particles aren't just electrons. That's like kicking out a helium nucleus. I say nucleus because there will be no electrons around the helium atom as it comes out, right? It's coming out as helium plus 2. It's just shooting out there, no electrons, again, high speed, except when you consider the mass of an electron, you're looking at something that's roughly 1/1750 AMUs, whereas a helium nucleus is literally like 4 AMUs. So you're looking at something that's like 4,000 times heavier and yet still coming out with so much speed. So alpha particles are huge. It's like bowling balls compared to ping pong balls when they exit the nucleus. So they really pack a wallop. And I know I'm going to be hitting information we have on slides coming later, but I'm on a roll. Just know that like when an alpha nucleus is spit out, the air around whatever it's coming out of is enough to stop an alpha particle completely to where it's moving slow enough it actually captures 2 electrons and it's no longer an alpha particle. It becomes just a helium atom. About 6 to 8 inches of air is enough to stop it. So that becomes important when we talk about safety concerns later on. Whereas when an electron comes out, much smaller, they can go through like 8 to 10 feet as opposed to 6 to 8 inches before they stop and become slow enough where they're just an ordinary electron or positive electron. So yeah, let's go to the next slide and I'll get back on track. Radioactivity is a recent discovery. So Marie Curie and Henry Becquerel are the scientists credited with pretty much getting nuclear chemistry off the ground. So Henry Becquerel was studying phosphorescence, which is like a process where, light's given off of a compound or an element that's undergoing phosphorescence. And what you're seeing, that light is being generated from electrons dropping from higher energy levels down to lower energy levels, all right? And phosphorescence and fluorescence are very similar. The only difference being that in one case, the electron is dropping down to the ground state, and in the other case, it's the electrons just dropping down to a lower energy state, but not the ground state. So you could have 3 or 4 energy states, and if it's dropping from 4 to 3 or 4 to 2, now you're talking phosphorescence, and all the way to the ground state, now you're talking fluorescence, or vice versa. I'm not sure which, but that's what's going on there. So he's studying phosphorescence. And one day he gets in a hurry, and the way he's studying phosphorescence is he's taking things that are phosphorescing and he's putting photographic plates basically behind where he's looking at these things, and he's developing how much energy is being deposited into the film, right? It's basically developing parts of the film, and he can put stuff in front of it and see shapes and all sorts of stuff. It's kind of like a cheap photograph where you don't use silver nitrate or any of those developing chemicals. You're just using the energy to create your image. And he had his film sealed in a bag, like foil, in the drawer, and then he put his chemical thing in the same drawer with it, and he left. He came back, and he developed the film having never run the experiment, just as, it was with the other film, and it still had like energy on it as if it had been exposed, even though his film was totally covered. And that does not happen with phosphorescence and fluorescence. And so he knew he was onto some new process, and he didn't know what it was. He called it phosphorescence only because he lacked the understanding, and we lacked, a good model of the atom to really know what was going on. So Marie Curie stumbled on his research and was interested in it, and she started trying to look at radium as a byproduct of uranium. And she was trying to separate things out to get to the bottom of what was creating this issue. And she stumbled on radium as an element by accident, not knowing that there was a mixture there of two different elements. So with a lot of careful separations and such with her husband, Pierre, they were able to actually figure out that, hey, this is not phosphorescence. This is something else. We're going to call it radioactivity and da-da-da-da. Yada, yada, yada. The quote Seinfeld. So these scientists are the ones that really increased our understanding of radioactivity, and they made us aware of kind of what it was and what was happening, but they still didn't know everything. It was just like this was the beginning of everything in the nuclear world. Let's go to the next slide. Radiation versus contamination. This is another safety thing. So radiation is the radioactivity that's being kicked out of a nucleus because it's unstable. Contamination was something, it's when something that is emitting radiation gets into or on something, meaning contaminating it. And now wherever that something goes, it's going with it. And so you continue to get radiation because you're not walking away from it because it's on you or it's in you. So everything we do around nuclear chemistry, it's really important that we try and stay uncontaminated because it's already a health hazard when it's hitting you. It becomes a greater health hazard if you're going home and it's still emitting and you can't get it away from you. When you talk about the big alpha emitters, like uranium and up, these elements chemically, mind you, not radioactive wise, not nuclear, but chemically, we typify these as bone seekers, meaning what they like to do chemically is they like to go straight to your bones and sit there. They don't necessarily excrete well. Now, uranium, you can excrete pretty good, through urine and whatnot. It's not going to hang on to much of it in your bones. But when you start getting into americium and plutonium and curium and these ones that go up the periodic table, you're screwed. Like it gets to your bones. There's no way to get it out is the problem. It's happy there. And you're going to carry that around and it's going to emit at your bones and it's going to do that until you die. And that's where you end up with chronic issues, bone cancer and whatnot that come from continuous exposure that you can't turn off. You can't turn off the exposure because it's inside you. So the greatest danger from an alpha emitter is ingesting it because that's when you can't get rid of it. Now, if you just get some on clothing, you can throw away the clothing, you're good to go. Or like when I'm cleaning up a fume hood where I've done experiments, if somehow I've gotten a little bit on the floor of the fume hood or on the wall, nitric acid, some cheesecloth, and you can get it all onto the cheesecloth, throw it away, and obviously not in a normal trash can, but that stuff can be cleaned up. So just know that there are two kinds of contamination. You can have internal contamination, meaning internal to the body, and you can have external contamination. A great example of external contamination and how it can be used in a very negative way is a lot of us have probably heard of the term dirty bomb. A dirty bomb is just an ordinary bomb. It's not a nuclear bomb, but it's a bomb that has nuclear material all around it, and it scatters it just to contaminate the area. And if you can imagine, you've got a bomb that like takes out a building or a city block, and now you've got all this contamination everywhere. It takes a long time to clean that up. And until it's cleaned up, it's all emitting to anyone that's walking by or around. So that becomes a bad thing. In fact, I would say it's almost harder to deal with the aftermath of a dirty bomb than it is just like a nuclear bomb. After a nuclear bomb, there's not a whole lot you can do to clean things up, and it's wiped everything out. Like it's just a nuclear explosion releases so much energy, but there's not much left. And then there are things called neutron bombs. Different than dirty bombs and different than what I would call a nuclear bomb, which would be either a fusion or fission bomb. When you deal with neutron bombs, that's where you're creating an explosion that releases a bunch of neutrons. And neutrons pass through things because they don't have a charge. They can actually go quite a bit of distance and through walls and stuff. But around metals, they tend to get absorbed, and then those metals will then change to different isotopes as they get absorbed. And now you end up with unstable isotopes of the same metal that is now emitting radiation. So you pretty much have to get rid of the metals that are exposed to continuous neutron radiation because of that. But a neutron bomb, they talk about it as like a clean killer, because you could detonate one and it could leave like buildings standing, but those neutrons they like to not hit just metals, but they love like hitting hydrogen. They're just drawn to it. It's chemically, there's just something going on there. We call it a cross section that makes it attracted to it. That's how we use to measure how the attraction of a neutron to something, by its cross section. Because most of life involves water, which is like 2 parts hydrogen, 1 part oxygen, it'll pretty much kill anything with hydrogen, which is pretty much all life as we know it. So a neutron bomb you could detonate and leave all the buildings and yet kill all the life. And still leave the area quite irradiated anywhere there's metal on top of it all. So that is everything I have to say on contamination versus radiation. So just remember, radiation that's what's being emitted from an unstable nucleus. Contamination is like everything that's left behind that's doing the emitting, if it's left on something. Next slide. And here I'm just talking about all that stuff. Obviously, as a result, when you're talking about handling radioactive materials, time, distance, and shielding are your best friends. If you limit your time, if you increase your distance from what's emitting, your safety increases with the square of the distance. So if I move back 3 feet, I'm 9 times more safe, that kind of a deal. So time, distance, and then shielding. Shielding just involves using something really big and heavy that's going to stop everything before it gets to you. And usually lead is what's used in shielding. Although, again, it depends on the type of radiation you're talking about. Like if you're trying to shield yourself from high-level gamma rays, which accompany a lot of this stuff, then lead is great. And so, you go to the dentist office, you get some x-rays, they have you wear a lead vest, and that's to prevent the x-rays from hitting, the lead stops most of the x-rays, and it just lets the ones hit your skull. And of course, a little bit of your brainstem and whatnot, however they pass through. But it's not hitting everything else like your major organs and things, because the lead vest that they have you put on. So lead's really effective at stopping x-rays and gamma rays. It's overkill for trying to stop beta and alpha, because you don't need it. Alpha can't even penetrate the dead layer of skin that's on your body at all times, let alone clothing and everything else. And beta particles can get into the body, and they usually deposit all the energy in your body, but they don't exit out the other side. Again, lead is overkill to stop those. You can stop it with stuff that's much lighter because they're so much smaller. But with gamma, yeah, lead is where it's at. So, and then in addition to time, distance, and shielding, which are used to help prevent contamination, we have other safety things that we put into place, like regular monitoring, storage and disposal, and how we do that, protective clothing. So like when I was in the lab working with all this nuclear stuff, I always had to wear full protective clothing. And what that meant was I would put on, shoes, not open-toed shoes, but full shoes, socks, pants, shirt. I would wear a lab coat that was long sleeve, so that the only part of my body that was exposed to contamination, if something were to get out, would basically be my face and my hands. And you can protect your hands with gloves, and we could tape those up. And at that point, it's just your face. And then for that, you usually lower like a glass, fume hood, and you can look through it to do your stuff and put your arms underneath it to manipulate things. But now you've got your face protected from, and the number one thing you're protecting yourself in that instance, it's not gamma because you're using glass, right? Not lead. But you're protecting yourself from accidentally ingesting something that might be in the air. So that's what all that's about. And then, of course, there are rules that protect against how we dispose of radioactive waste and sources and whatnot. There are different kinds of radioactivity that we consider for disposal. We have low-level waste and high-level waste. And these are defined very oddly, but they make sense if you're in radioactive waste management. And I've taken some courses on that in grad school, along with hazardous waste management and such. Basically, you can think of it this way. If it's a medical purpose, they call it low-level waste. And if it's coming from a nuclear power plant, or a power plant designed to create bomb grade material, those kinds of isotopes, then we call it high level waste. That's literally the distinction they make. It's by the application that they define it, as opposed to by the isotope, which is counterintuitive to how we define safety for all hazardous materials, which is those are defined by the chemistry of things, as opposed to radioactivity, which now you have chemistry and radioactivity. It's like you got multiple things to consider. So because they don't want to like lock themselves into one or the other, they go by application. And as luck would have it, it's only the nuclear power plants and missile silos and whatnot that use the real bad high level. I say high level, and it sounds stupid because now I'm using it to define the term, but that's the stuff that's putting out the real high energy gammas and the real nasty isotopes that if you ingest, you're not going to get them out of your body. It doesn't have a natural way of removing it from where stuff wants to go. So it works out. The definitions do, but they are kind of counterintuitive to what you would expect. Let's go to the next slide. Production of radiation for medical applications. Notice I said production of radiation. So we use radioactivity a lot in diagnostic applications for imaging and whatnot. We also produce isotopes specifically to treat stuff, but we're after the radiation that the isotopes are producing and not the other way around. So we're starting with the radioactive bit first, so I decided to lead with radiation rather than, it gets old using the word radioisotopes over and over and over again. Proceed. So nuclear reactors and cyclotrons are the main tools used to produce radioisotopes in healthcare. Know that a radioisotope, that's just a fancy word for an isotope. This is radioactive instead of being stable. So like I said, hydrogen-1, that's stable. That's not a radioisotope. That's just an isotope. But deuterium and tritium, those are unstable. We would call those radioisotopes instead of just isotopes. They're all isotopes, but only deuterium and tritium would be considered radioisotopes. That's how you would look at it as far as subsets go. So with cyclotrons, you basically are accelerating charged particles in an accelerator. And in cyclotrons, you can fit into a lab. Like they can be like a 3x3 foot, cube, or they can be even smaller. I think I've seen them as small as maybe 2 feet long, 1 foot tall type, 2x1x1 kind of an instrument, where they're producing, specific energy X-rays and gamma rays for looking at stuff. These are great. Generally, you're not using those to produce the isotopes themselves, although it's not to say that they can't be used that way. It just depends on what isotope you're trying to produce. Next slide. And by the way, nuclear reactors, the way they do it is when you have a nuclear reactor, you're putting your fuel like within a moderator so that you keep reactions under control. Like in the case of fission, that's how nuclear power works. But when you're not concerned with creating power, and you're not using fissionable elements, you're just interested in creating isotopes through, shooting neutrons or beta particles or alphas at things, you no longer have to worry about a nuclear explosion when you're dealing with anything but fission. So keep in mind that like you can build nuclear reactors that are designed to produce isotopes that don't produce or use fissionable elements like uranium and plutonium. If you have a reactor designed to produce those, and power reactors use those and produce other bad stuff, then you've got to have major safety stuff involved, right? You got to have a containment building. You've got to worry about keeping the reaction under control, because if it gets out of control, when you suddenly have a nuclear explosion right there at the power plant itself or at your, isotope producing plant, like then it becomes a thing. But when you're only looking at producing stuff like we produce, like iodine-131 and some other common isotopes used in the medical field, you're no longer building a power plant to do that. Instead, what you're doing is you're running. An easy way to look at it would be to take something like iodine and say you take the natural form and you want to produce an isotope that weighs 2 more. You could literally just shoot neutrons at it until it absorbs them and boom, you've got it. Or you could choose an element underneath iodine where you want to increase its atomic number by 1, or choose an element above iodine by 1, and you can get it to decay to come down an element to where you need it to be. But when it comes down, it now becomes a different isotope of what's there. And I could go into that. I don't think I include the best way to illustrate it is there is actually a periodic table that exists of isotopes, and it's the hardest thing to look at because you really need like a 9 by 12 foot desk to spread open this table, even when it's small, because it will list stuff as if it were in the periodic table, but it has space for each element to have anywhere from 2 to 10 different isotopes depending on the element, like all the way through horizontally without running into the other columns. It just gives you the space to do that. It's they're really amusing to look at. And if you want to, definitely Google like a periodic table of the isotopes instead of just the elements, and they're fun to look at. So at any rate, again, I'm going to emphasize all these isotopes are the same element. They behave the same chemically. That can be a pain for doing separations when you need like a real pure sample to then, inject into a patient, or a real pure sample so that it's only giving off the radiation you want. So that diagnostically, it's only producing what you want, so that you're getting something that makes sense when you're looking at everything. At the same time, we can use that to our advantage, because a radioactive form of iodine, well, the thyroid, you can have thyroid cancer when you're not getting enough iodine, or you're getting too much, or like these things can come up. You can inject a radioactive isotope of iodine, and it behaves the same way as regular iodine, so it goes straight to the thyroid, and then it's emitting that radioactivity around all the bad stuff in the thyroid. And eventually it because of its half-life, it reduces back to a non-energetic form of iodine, one that's not radioactive. And in the meantime, all it's done is destroy like the bad cancer that's right there. And you don't have to do anything special about keeping it in the area. It's literally, you can chemically send it to the area. Those kinds of isotopes, radioisotopes, are great when you can have them. Not everything is so specific as iodine is to the thyroid, but where it is, we certainly take advantage of it. So yeah, when I say process to purify the desired isotope, know that you're not chemically processing a lot of times, but you are also chemically processing a lot of times. So if you want a pure sample of iodine-131, when iodine decays, it becomes another element. So you need to do some chemical separations to get rid of the element you don't want, so that you have a pure sample of iodine to actually use. And obviously you want enough of that isotope there. They basically give you enough iodine at the start of the isotope you need, and you just have to do a separation right before you use it. And that's how we go about it. And then depending on the half-life, as long as you use what you've purified within, in some cases you have to use it within the hour. In other cases, you can do a separation to get rid of these other elements, and you might have days to use it, or weeks. It just depends on the isotope. All that is very specific to each isotope, not to each element, but to each isotope of each element, because each isotope has its own nuclear properties, even though the chemical properties are the same. Next slide. I'm probably going into way too much detail. Why don't I stop and take questions? We'll go to the next slide, and then let's just pause and take some questions, if there are any.
There is.
Read them off one at a time if they put them in the comments.
Would you like it after the next slide or no?
Oh, you can advance to the next slide and then go ahead, and we'll just leave the next slide up.
Kimberly asked, is it safe to use tritium on weapon night sites?
On what?
Weapon night sites?
Weapon night? I don't know what a weaponized site is. A weaponized site. Oh, okay. So here's the deal with tritium. There are two kinds of nuclear explosions, or two kinds of nuclear processes that involve, well, there's We have something called fission. We use that for power. That's where you take uranium or plutonium and you split the atom. And in the process of splitting it, you get two new elements, and they're asymmetric. So you can't just take half of a uranium atom and say, okay, you've now got two of element 46 instead of one of 92. Fission doesn't work that way. You always get an asymmetric distribution, but you're going to end up with something that's, bigger than 46, one less than 46. So you might get element like 38 and element 52 type of a thing. And if I had that memorized, I would tell you what that is, but I would have to go look it up. But it's irrelevant. With fission, the atom is split, and in that split produces neutrons, which then get absorbed by the other uranium atoms around it, which then become more unstable than they already were, and then they split. And then those create neutrons, and then they split and split and split. And you can imagine you go from 2 to 4 to 8 to 16 to 32 to 64. You quickly get a ton of neutrons around. And if that goes uncontrolled, you have a fission bomb. That's what was dropped in Hiroshima and Nagasaki. The only difference being one was uranium bomb, one was plutonium bomb. Both were fission bombs. Within 5 years, we developed what's called a fusion bomb. A fusion bomb, instead of splitting something apart where you're starting with something that's fissionable in the first place, now you're actually putting hydrogens together to form a helium nucleus. And you're fusing them together. So two H's will become a He. They become a helium. And when you do that, you get a ton of energy. In fact, you get more than you get from fission. We would love to have a fusion power reactor, but right now we have to put more energy into the reactor to keep it stable than we get out of it. So it's not commercially possible yet. It's possible. You're just not going to generate power. You're going to use more power than you create. With fission, we can create more power than we use because we're not putting any power into it. We're just putting the elements close enough together that those neutrons hit each other and you get the reaction. And then you use something called a moderator that absorbs just enough of those extra neutrons to keep the reaction going. We call that criticality, when the reaction gets to keep going. But you keep it at a rate where you're just over-absorbing enough to get the next one to start rather than getting like 10 and then 100 and 1,000. You're keeping it from doing that, which is where it becomes a bomb. So with fusion, you don't have to worry about that. However, you don't just necessarily put together two hydrogens to make a helium, because if you put a hydrogen and a hydrogen together, you end up with two helium. And what I mean by that is a hydrogen weighs 1. So two hydrogens put together would make helium that weighs 2. But stable helium weighs 4, not 2. So now you're putting together two stable things to make something unstable. Not only is that hard because the nucleus doesn't want to do that because it's unstable. It's damn near impossible. So unless you've got like a huge particle accelerator, that's just not going to happen. But what you can do is you can put together a hydrogen with a tritium. So you take hydrogen that weighs 3 and put it together with hydrogen that weighs 1, and now you're getting helium that weighs 4. That's tritium. So when you do that, and you're talking about nuclear bombs, we call that bomb and that fusion bomb, we actually call those hydrogen bombs. And that's because you're using hydrogen as your fuel source for the bomb. And you're using not just hydrogen, you're using hydrogen and tritium. The problem with tritium is it's got a half-life of like 15 years. It's a real small half-life. So you have to constantly replace that tritium in those bombs to keep the bombs viable. Because after 15 years, half the tritium that was there for things to go off, you've now lost half of it. It's become stable hydrogen. So you're getting yourself into that situation where that bomb is no longer going to function the way it should. It's not going to create a fusion reaction because you don't have the right fuel when you lose a lot of that tritium. So I think the question was, is it safe to use tritium in a weaponized factory or something like that? My gut response would be no, that wouldn't be so smart. But remember, for this tritium to actually fuse with the hydrogen, you've got to have that happen in a small area. You basically have a bomb with shaped charges that are all directed inward. So you collapse the hydrogen and tritium together into such a small space that they're forced to react because they're not going to react on their own. Why? because hydrogen and tritium are the same chemically. So they're not going to ever combine on their own. I mean, they can combine to make H2, but I mean, that's where you have one H and a T together as like a hydrogen gas molecule. Like chemically, they can add and do that, but there's no strong like radioactivity. Like tritium by itself is not all that big a thing. Y'all have probably heard of heavy water, which is used to moderate normal power reactors too. Heavy water is just hydrogen with an extra neutron on your waters. So if you have oxygen and two hydrogens and that's water, replace one or both of those hydrogens with deuterium instead of hydrogen, and now you have heavy water. They don't ever use tritium because it's not worth the effort to do what they're trying to do. And what they're trying to do is, remember I said hydrogen likes to absorb neutrons? Well, yeah, the deuterized hydrogen, the deuterium will absorb neutrons even better than regular hydrogen. It's got a bigger cross section, so that's why they like to use heavy water in power reactors. But all those things don't stay heavy forever. They don't stay radioactive forever. The whole purpose of radioactivity is to take an unstable nucleus, get rid of something usually. You can combine it with something sometimes. But the main idea is you're going to eject something and then make it stable because you've changed the neutron to proton ratio to make it more stable. And I didn't comment on the neutron to proton ratio, but outside of the first element or two, generally speaking, a stable neutron to proton ratio starts at about 1 to 1. With hydrogen, obviously it's the exception because it has a 1 to 0. You can't even get a ratio; it's undefined. But when you get to helium, the stable ratio is 1 to 1. And as you work your way up through the 82 elements that are stable, that 1 to 1 slowly works its way up to a little over 1.5 to 1. And after that, that's too many neutrons to protons to be stable. And every element past 82 is radioactive. They don't have stable forms. They don't have stable isotopes. All their isotopes are radioactive because they all end up with neutron to proton ratios that are either too big. That also works the other direction, too small. You can be neutron light. And so if you can picture a diagonal, almost like a parabola curve that goes from 1 to 1.5 on the neutron to proton ratio, to either side of that stable curve is where you're going to be in the radioactive area. And it's just along the swath of the curve that's got that stable ratio where you're not radioactive. I hope that answers your question. Tritium isn't that bad of a ionizing element, ionizing isotope. It's radioactive, which we'd like to say everything radioactive is bad, but it's not. If you walk out of your house and it's raining, you can set off a Geiger counter with alpha particles because radium, which is naturally soluble in water, it's also radon is a gas. It will come out of the ground and go into the water, and then you track it in on your feet, and you can scan your feet with a Geiger counter, and next thing you know, your feet are showing radioactive. I had to deal with this all the time. Every time I walked into Oak Ridge National Lab, I was working at the Transuranic Research Lab, a very small building. And I had to pass through 3 airlocks, and I had to go through multiple detectors. And if I went into the building and turned around and wanted to leave, I couldn't because I would show up as tracking radioactivity out because I had actually tracked it in on my feet, just that gas. Fortunately, the half-life is very short. And as long as I waited about a half hour, it would decay enough where then I could get out and not set off the detectors. So, but they wouldn't let you out until that had gone away. So, we're around radioactivity all the time. We just don't think about it. There's uranium naturally occurring in the ground around us, more so in some places than others. Like the soil in and around Colorado is higher in uranium content. It's actually where we mine a lot of uranium. And so you're going to have higher radon gas tallies around there because radon gas is something that comes out of uranium decay. And I don't mean spontaneous fission. I just mean like normal uranium-238 trying to decay to get stable. Uranium-235 is the isotope that undergoes spontaneous fission. Actually, might be 233. And with plutonium, again, you can have plutonium-241, which is pretty stable. It's radioactive, don't get me wrong, but I mean, for all the isotopes, pretty stable. But to get the spontaneous fission isotope, because not all isotopes of plutonium and uranium undergo spontaneous fission, there has to be an allowed route there. those ones are very specific, and so you have to have them around to get that fission. That's what made making the bombs so difficult back in World War II. We couldn't chemically separate uranium-235 from uranium-238. Uranium-235 and uranium-238 are chemically identical. So the only way you could separate them was you'd have to run fluorine gas over uranium ore, and there would be chemical reaction to make UF6, uranium hexafluoride, which is also a gas. But now you would have UF6 where one molecule of UF6 might be with uranium-238, the other would be with 235, which is lighter. And then you would use magnets to basically pull these ions, because you could ionize this gas. You could pull them around and around and around through a series of filters, and eventually the heavier stuff would lag behind the lighter stuff because it moves slower. And then you could just every now and then cut things off, pull off a chunk, and then continue to run the other stuff. And chunk after chunk after chunk, you can purify the stuff. Understand that for a bomb, you need it to be 90% of that fissionable isotope, and that natural uranium only has 0.3% of that isotope. 0.3, and you got to get it up to 90 times, and you can't do it chemically. You have to do it through gigantic brute force physical fancy means. So this is not something that like people can't make this stuff. No one has enough money to build the stuff to do this stuff. Countries can do this stuff where you have massive GDPs and money that you can throw into creating facilities designed to do this. So it's not something you have to worry about insofar as someone else just creating it. It's a lot easier just to go steal it. So again, how you store this stuff becomes very important because you don't want it stolen either. Next question. I know that one was a long answer.
That's all our questions for now.
Cool. I'll keep them short.
For your great explanations.
Yeah, let's cruise. So yeah, quality control. Again, like I said, every time you have a disintegration and you get that radiation you want, you've now created an isotope of a different element that you don't want. So quality control is really important. There, a lot of times these things, you do have to do a quick chemical separation to use it so that you're getting rid of stuff you don't want to inject in the body. Very, very important. Next slide. I ended up with a presentation I think that is way too big. All right, diagnostic applications, radiology. So we can visualize stuff, and everyone here is familiar with x-rays. So CT scans and MRIs, these are fancier than x-rays. You can almost think of a CT scan as you drink something that's going to be emitting a certain kind of radiation, and then you run your body into this tube, and that tube has detectors all the way around it in a circle, and it's able to pick up radiation as it basically annihilates itself. Like a positron eventually will lose all its energy after hitting things, and it will then go kaput and become just two energetic beams of like half the energy of what the mass of an electron would be. So they're really easy to see because they show up as like, I think it's 512 mega electron volts on a detector. And so by drinking a specific isotope that isn't going to stay in your body. So like, again, I hate to scare everybody because not everything is a bone seeker, but I've worked around a lot of alpha stuff and it all was. So I was just trained to be scared of very specific alpha emitters. The stuff they're using is not like that. It's stuff that you will eventually pee out, or it's got a half-life where it's going to be gone and out of your body. It's not going to sit there and continue to emit. But they'll put it in, and it'll run through the digestive tract and everything else, and it will emit as it goes. And this will generate an image as detectors all around your body pick it up at different points. It puts together a three-dimensional picture because different detectors are picking up the same thing at different times, and they're exactly 180 degrees apart when they annihilate. So you can figure out a 3D map based on that. And MRIs use similar technology. So it's, wish I had left myself more time. At any rate, these are things that we can use to diagnose stuff. That's specifically imaging created from gamma rays and x-rays. You can also use radioisotopes with these imaging techniques that use gamma and X-ray, where the specific radioisotope, you're not looking at it emitting radiation and it annihilates and gets, but where you're not 3D mapping, but you can use it to check into what's going on biologically, because you can say you're interested in a process in the heart, and that process in the heart that you're looking at specifically has metabolites, between beats that's being produced, and so you find the right isotope chemically, the right element chemically, and replace that stable form of the element with a radioactive one, and then you run it through that process. Now you can see what's going on with an imaging technique and a very specific piece of something given someone in the process itself, and you can get some lifetime data as stuff is metabolized by the body and where it's going. So there are some real neat tricks you can get out of all this stuff. Next slide. Technetium-99, there's a little M there. It just means metastable. Basically, you can have technetium-99 ground state, and you can have technetium-99 like heightened state. It's got a little more energy. Technetium-99 is just a metastable state, but when it decays to the ground state, that also gives off a real specific radiation burst, so to speak, that we can pick up and check out. The half-life is only 6 hours, which means it's in and out of your system real fast, so you're minimizing radiation exposure to systems that you don't want to expose, but that are a part of it when you're using things like this. I mean, our goal should be to always use an isotope where it goes straight to where you want it and never goes anywhere else if you're going to internalize it. That's not always possible. When you talk about treating people with radiation itself as opposed to with a radioisotope, you're hitting like everything on the way to whatever organ you're treating and a lot of healthy tissue around it. Fortunately, with things like cancer cells, they're more susceptible to radiation than healthy cells. And so they die quicker around radiation than healthy cells do. So it becomes survival of the fittest, where you pound stuff and hope that you kill enough of the bad stuff faster than the good stuff that you see an overall better result. But when you're doing stuff like that and using just pure radiation to treat something in the body, it is having to pass through the skin and everything else to get there. And so you end up with, like burns and things like this. And when I say burns, I mean like sunburns and, some dry skin and there are definitely some health effects, but I think radiation is a lot more targeted than, say, chemotherapy. Chemotherapy is more of a chemical treatment, not a radioactive treatment, but it's like throughout the body. And so you end up with a lot more symptoms. But then there's some things that respond better to chemo. So, not everything is radiation. That's why we have MDs tell us what's best, or at least give us suggestions. Technetium-99 is also a radioactive isotope. So not only does it emit stuff when it goes to a stable state, it also emits gamma and stuff that we can look at. Again, it's optimal because we're limiting exposure because the half-life is so short. Next slide. Positron emission tomography, PET scans, SPECT scans, single photon emission computed tomography, real fancy acronyms. If you're in the medical field, you've seen PET and SPECT before. Positron, that's cool. That's a positive electron. I just love positrons because no one ever knows what they are, but they're just positive electrons. That's what you get when you're on the other side of that neutron to proton ratio. So if the neutron to proton ratio is too big, you're generally getting beta decay. If it's light and you don't have enough neutrons per proton, it goes the other direction. You emit a positron in order to get heavier, in order to get more neutrons to protons. So I just love talking about that. It's the same as everything else. It's just in fact, it's PET specifically I was talking about earlier when I talked about positron electron annihilation. We have electrons all around us. You don't have positrons all around us because when they slow down, they immediately find an electron and boom, it's gone. It's literally like matter and antimatter. Anybody know why we don't have antimatter around us? If we did, it would immediately find matter and boom, it would gone. It would annihilate itself. We have almost all matter in this universe and almost no antimatter. That's not to say we can't create antimatter. but it doesn't stick around long because there's too much matter around and it immediately finds something to react with. That's the deal. That's I mean, it might be a little more complicated than that, but honestly, it's not. It's just that easy. So it's a good thing too. We're not in a universe that's 50-50 because we wouldn't be here if we were. We would be in a universe with just nothing but explosions and hopefully stuff recreating. So next slide. Therapeutic application. So here now we're not talking about imaging. Here we're talking about actual treatments. Next slide. So when you treat, now you're getting a targeted radiation to a very targeted site. Iodine, radioactive iodine being used to treat the thyroid has to be one of the best examples of how we can be very specific and we allow the chemistry of the radioactive isotope to carry it exactly to where it wants to go. And then the half-life is short enough and yet long enough that it can sit there and kill stuff. And then after a little bit, it's gone. And then you either need another treatment or you don't, but it's not like continuously there. It's just iodine, right? So it's fantastic. There are a lot of other things that I've seen used too, and you don't have to ingest them. For instance, I've seen ovarian cancer treated by taking an alpha emitter. Remember I talked about alphas? They're like bowling balls. They're like huge compared to something emitting an electron or a positron. Alpha particles are just 2,000 times this, or 4,000 times the mass of an electron. And they, like I said, they can be stopped by the layer of dead skin on your hand. Like they can't even get through you externally. The only way they become a problem is if you ingest them. And like I said, most alpha emitters are bone seekers, so you don't really want to be around them. Well, I've seen alpha emitters where they take an isotope that emits alphas and they encapsulate it and put it at the end of a rod, like a titanium rod. And then they'll insert the rod and put it right up against the cancer on the ovary. And now you're smacking that baby with alphas instead of smacking it with electrons, that cancer. And it packs a wallop and it does a number on the cancer. And in cases where you have cancer tight knit together in one spot like that, that's a technique that works really well. It also is minimally invasive and it does almost no damage to anything, because alphas get stopped by almost nothing around it. They don't go anywhere else. The problem with a beta particle is it'll get through most of the body and then deposit its energy. You can choose different energy betas to get them to stop and deposit the last of their energy right where you want to hit something, but it still has to pass through everything else to get there. So it's still doing damage along the way. Using rods and alpha emitters is kind of a nice way to split the difference, where you can get fancy, but you're not having to internalize it, where you can't just remove it. Because when you remove the rod, you've also removed the alpha emitter. So you're not left with something that's contaminated. There's no contamination left behind. So yeah. Yep, we're almost done. Go back one slide. I think I saw iodine 131 there. This is a beta emitter that's used a lot, iodine. I talked about this with thyroid. Advance the slide. We're almost done. And then I was just talking about targeted radiation therapy. That's where you're taking beams of X-rays and gamma rays and putting them right. There's some things you can't get to easily, but have no isotope that's chemically nice for what you want to do. Brain cancer is one of those. If you're going to treat brain cancer, a lot of times you got to go this route or chemotherapy, and both are crapshoots because you're having to hit so much healthy stuff around it. But again, you can control the size of that beam, so to speak, with radiation, which makes it a little more targeted than chemo for parts that are more responsive. But again, more responsive is tomato, right? It depends on what specific thing you're looking at. Next. I think we're almost done. Yes, I made it. We can do more questions. We're at the end of our time. I did not leave enough time for questions and talk too long on the wrong stuff, I'm sure. So any questions anyone has? There's a lot here to suck up.
Kimberly's asking, what do you suggest we do next in therapy?
Oh gosh, with therapy, it's continuing to find ways to tighten beams, use different isotopes that don't react as much with things that we're putting them through, find things that are excreted by the body faster than other things that we might be using for the same treatment. Chemistry, just chemistry by itself, the world is your oyster, right? Just finding certain molecules that, we create pharmaceuticals from molecules, right? And then we ingest those molecules and it's supposed to treat an ailment. So experimenting with different isotopes within those molecules and seeing what can be an added benefit versus a detracting. I guess it wouldn't be a benefit if it's detracting from the issue, but it's figuring out what could be more of a benefit and less of a hazard. That's really where most of the research is at when you're talking about the use of radioisotopes specifically for therapy. Chemically, we know what's going on everywhere, so we know what we like to target and what we have that's easy and what's hard. As far as the diagnostics, that's the stuff that's really going to get like the most advancements. Like if you're going to ask me where were the greatest advancements being made in nuclear chemistry as it relates to the medical field, the most advancements are going to be made in diagnostics. That's where we're going to get fancier detectors and different isotopes we can use to generate, a better picture, especially 3D pictures. That really helps a lot. And being able to use more radioisotopes when looking at the process itself and what's going on. The way my body metabolizes, for instance, fat versus protein versus something else, like you can't really just show an image of that going on. Like sometimes you can do like an iodine print and grab some cells but like in vitro, like as in situ, as it's happening, that's really hard to do chemically. But with something like an isotope, you can literally do it in situ. You can be watching it real time as it's doing stuff. And you can use these radioisotopes as part of the molecule that you would normally be ingesting because it's identical, but now it's giving off radiation you can detect and you can watch what it's becoming and where it goes. That's like the other side of it. That's less diagnostic. Well, that's still diagnostic. It's not so much therapeutic, but it helps in figuring out the therapeutic treatment that you're going to have that may or may not involve more nuclear chemistry. So diagnostics is where it's at. Other questions?
It looks like we've hit all our questions, Eric.
All right. I just want to leave by saying nuclear chemistry, regular chemistry involves making and breaking bonds. So you're creating new molecules in the process of doing that, or you're breaking down old ones. Nuclear chemistry involves a change in the nucleus because the nucleus is unstable. You can take a stable nucleus, make it unstable, and force it to break into something stable that is what you want, and you get something out of that. That's where nuclear stuff can be really helpful. It's not just something we use for power. It's not something we just use for bombs. This is stuff that we really have been using to make a difference in imaging issues, trying to figure out how to treat stuff, and then used in the actual treatment. Like there's a lot there, but its limitation is also its greatest strength. And that's the fact that different isotopes behave identically to their other isotope counterparts because they're the same elements. They don't behave differently chemically. They behave different nuclearly. Not that that's a word, but it's their nuclei that are behaving differently. And each isotope is giving off different types of radiation in order to become stable. One isotope might emit a positron to become stable. One might emit a negatron to become stable. One might emit an alpha particle to become stable. Some will absorb neutrons to become a different isotope. They don't change into another element. They just absorb the neutron to get heavier, but that might make them more stable. Others might kick neutrons out to get more stable. Again, they don't become a different element if they're kicking out a neutron or accepting a neutron, but they are getting heavier or lighter, which helps that neutron to proton ratio. There's a lot going on there. And not anything can happen. Like you can't take uranium-235 and decide, well, I'm going to force that to do alpha decay. Like if it's not already set up to be stable to do alpha decay, it won't. There are only certain routes that are energetically allowed. And when I say energetically, I'm talking like nuclear energy energetically allowed. It's almost like electron configurations. There's some that are allowed and some aren't. It's the same thing with the nucleus. It has its own version of an electron configuration. It's called nuclear configuration. And there's spin and parity things and stuff that is way beyond the scope of this lecture, but it controls the route. And so it sounds, on the surface, it can sound like we can do anything. And the reality is, like, these things only do a certain thing a certain way, and that's it. Like, there are no surprises. We know everything going on. It's just using what we know going on to our advantage. So I guess I'll leave it there if there are no more questions. It's been a pleasure. Always is.
Thank you so much, Eric, for joining us for National Chemistry Week. Everyone is saying how wonderful and how great the explanations are. We found it quite fascinating. So thank you so much.
Yeah, I probably diverged a little too much, but